top of the hour. I'll go ahead and get started. I know people will be dialing in, and I'll let them all in. First of all, I wanted to thank every one of you for joining us for our first seminar for 2022, the virtual seminar from AIAA Hampton Roads. And also wanted to thank Dr. Amzajerdian for being our speaker today on a very exciting topic about navigation Doppler Lidar. Now, just to let everybody know, this meeting is getting recorded, and we will be posting this recording on online on the AIAA Hampton Roads YouTube page soon. So if you miss any part of it, you should be able to catch up on it. This is also an interactive session. Farzin, I'm going to unmute you, or you can unmute yourself, I guess. Do you want me to ask questions at the end, collect them at the end, or do you want me to ask them as you're going through? What would you prefer?
No, I don't mind to be interrupted at all. Let's do that. Let's just question, not to hold off, because yeah.
No problem. So I will serve as the moderator to let the person know that they can ask Farzin the question, but it sounds like Farzin is willing to kind of stop in the middle and take questions. So we'll do that. And if you want to also put your questions on chat and not want to ask it, I can ask it for you as it goes. So we'll be somewhat informal here. I don't know if there is a dial-in number or not. It should have been in the meeting invite. I think there is a dial-in number. If you go back to the actual meeting invite that you got after you registered, you should have that. I'll also put that in the chat here in a bit, right after I introduce introduce Farzin here. So we'll start off by saying thank you again for coming and talking to us about NDL. Dr. Farzin Amzajerdian has been working on laser remote sensing technology for more than 3 decades, starting with his PhD work and continuing at Lytton, Raytheon, and University of Alabama in Huntsville. He's been working here at NASA Langley since 2001 and has been leading several LiDAR projects on measurements of Earth and Mars atmosphere and aiding landing missions on planetary bodies. He's currently the PI of NDL, Navigation Doppler Lidar, the actual focus of the talk today, and 3D imaging flash LiDAR projects aimed at enabling precision landing, hazard avoidance, and terrain relative navigation. He's also a fellow of the International Society of Optics and Photonics, SPIE, and he has chaired several international laser and LiDAR conferences and authored or co-authored more than 160 publications and 15 patents. And with that, please take it away.
All right. Thank you for the introduction, and thank you everybody for your time and interest. So I'm presume, let me see if I can. Oops. Okay. Let me see here. You see my screen, right?
Yeah, you're in just normal slideshow. If you want to go into slideshow mode,
yeah.
I think
Okay, let me see if I can fix that. I thought I was. No, I completely. Oh. Strange. I thought I'm here on the slideshow, but you don't see a slide presentation.
No, we're seeing your second slide. We're seeing Navigation Doppler Lidar right now. If you want to just stay in this mode and talk, that's fine too.
Okay, but okay, it shows up okay. Okay, let me give me 1 second. Let me see if I can fix that. Ooh. Okay, how about now?
It's still good. If you just want to continue on, that's fine.
Okay, all right. So navigation Doppler Lidar is just a laser sensor for that we built for the to assist with precision landing. It provides the vehicle vector velocity, the XYZ component of the velocity and altitude data. It comes on about like 5 kilometers altitude, and it starts making measurements that throughout all the way to landing. It's it can be viewed as a replacement of the radar sensors that were used in the past landing mission, providing similar type of data. But of course, being a laser sensor, the precision is going to be much higher. And we get to that a little bit as the differences with the radar. So let me first just explain how it works. That might help throughout. Um, the system uses a FMCW technique. Essentially, what that is that's, by the way, FMCW is frequency modulated.
Farzin, if we're still seeing your slide, title slide. I don't know if you have moved on to other slides. Just wanted to point that out.
I did. Oh, okay. So, all right. Let me move to a change my. Yeah, maybe it's because I have a split screen, and maybe that's the problem. Let me just move to one screen and that see if that works better. Oops. Okay. Now with the.
We're seeing slide 3.
All right. Okay. So slide 3. Yes, that's correct. Okay. It should look fine now. All right. So essentially, for the way it works is that if you see the plot on the lower left, you see a frequency waveform, like a trapezoid shape. You know, just imagine the blue or the black is what we transmit. You know, the y-axis is frequency, the x-axis is time. So we send out this waveform, and then what comes back, that would be the red plot, would be delayed in time for the time of travel of the beam to the ground and back. And then it's shifted up or down depending on the Doppler shift, because due to the velocity. So at the receiver end, we mix these two waveforms together. We have an optical heterodyne essentially. So what you get is that 3 frequencies corresponding to each of those 3 segments of the frequency modulation. And I show that at the bottom in the frequency domain. So then we just do a FFT on the signal and figure out those 3 frequencies. And from those 3 frequencies, we can get the range and velocity along the laser beam. The key is that the velocity is extracted from the Doppler shift of the laser frequency, and the ranges are extracted from the time of travel to the ground and back, right? So the velocity measurement is not the range rate, it's the actual velocity. And that's one of the reasons we can get such a high precision for velocity. And the block diagram shows how the system works. You know, we start with a laser, small laser. We do the frequency modulation to generate that waveform. We take part of it, amplify it, and we transmit it through 3 different lenses in 3 different directions. And then the return from the ground collected by the same lenses, and then directed toward the photo receivers, where we mix it with the other part of the laser beam. You know, that's where we mix those 2 waveforms together, we get the different frequencies. And of course, we're going to need 3 line of sight measurements, because in order to extract the velocity vector, the XYZ component of the velocity. And the 3 range data to the ground is used to get the altitude data. And we don't need the attitude of the vehicle to extract the altitude, because we have 3 measurements. Essentially, we just put a plane through those where the beam intersects the ground, and we draw a normal to that plane, and that would be the altitude. Okay. So we've been working on this system for a while. Um, and throughout, we've been doing testing, and improving the system. We did a proof of concept in 2008 where we flew this on a helicopter with racks of instruments, and it was just a proof of concept system. Then went from there to a breadboard, from there to a prototype, and now we have completed building the space flight engineering test units. And you see all the testing we did to demonstrate the capability. Also, we use these tests to keep improving the system. So later this year, we're going to have two of those engineering test units, ETUs, be flown on two lunar landing vehicles, one built by Intuitive Machines, the other one Astrobotics. Yeah, so we actually built four copies of those ETUs. One we use for just general testing. We do integrated testing for the landing with the band landing vehicles, and we do flight tests with them. We did one aircraft test a couple of weeks ago. We did a helicopter test last week. There's another helicopters going on this week, and then in 2 weeks there's going to be another aircraft test. So it's a lot of testing being done, to work out the interfaces between these sensors and the other avionics on the landing vehicles. We used one of them last year.
Farzin, are you? I would say that we're still, most of us are still seeing slide 3. I just wanted to make sure you're changing slides, and if you are, you do that on the screen as well. I'm not sure.
Okay, I don't know how to fix that. Yeah, I'm up to slide 5 now. Okay. What if?
Yeah, you might be sharing. Yeah, I think you're now sharing the right screen, and I think we will be fine. Somebody pointed out that the screen capture might be. I think we're now good.
We're good. Okay, you still see a full screen. Okay, I changed the mode.
So. We do, and you see your slide 5. Yes.
All right, beautiful. So, like I was saying, we flew another one of these on the Blue Shepard, New Shepard, the Blue Origins New Shepard vehicle last year. We did actually 2 flights on that, the suborbital flight. We delivered the other 2, the number 3 and 4, to those 2 lunar landers last calendar year, and they are currently being integrated. And you see a picture of the system, the ETU here. Everything is housed inside the chassis, and then there are 3 fiber cables that brings the laser light from the chassis and then hooked up to this assembly, the optical head assembly that has the 3 lenses. So the laser beam transmits through those lasers, and then the return collected by those same lenses, and then sent to the chassis through the same fiber cable, and then it's processed. So everything is inside the chassis. So on the vehicle, we can place the chassis anywhere that is most convenient for the landing vehicle. But that optical head has to be mounted such that it has, of course, a view of the ground. And they don't need to be close. They can be, that fiber cables could be 10 meters long, so it can be any length, really. The picture I'm showing on the 2 landers, the one on the right, the Intuitive Machines vehicle, you can actually see the chassis and the optical head on the side of the vehicle, and they're placed pretty close in this case. For the other landing vehicle, it's not clear because the chassis is behind those panels on one side. This one has a much longer cable, it's like a 3 meters cable. And then the head is on the other side of the vehicle, pretty close to that engine bell. I mentioned that this could be a replacement of radars that were used in the previous landing missions. The NDL operation is probably closest to the radar that was flown on the MSL, the Mars Science Lab. When was that? It was launched in 2008, and then more recently used on Mars 2020. That radar was installed on like a surfboard. It's 4 feet long. All the electronics on the top, as you see, and then there are 5 antennas, and they are pointed in different directions, like we do with our 3 beams. Pretty extensive in size and and dimensions. Essentially, we are replacing all that with that electronic chassis that you see on the top of the surfboard, and the optical head would be essentially the size of one of those 6 antennas. But not only is it smaller, though, the measurements, which would be much higher, precise, precision would be much higher by almost an order of magnitude. But perhaps more importantly, the quality of the data in terms of false alarms and dropouts. Being a laser instrument, the beams are essentially pencil beams. They're not like radars that the beam diverges. So the footprint on the ground would be very small. Like if you're like from 5 kilometers, the laser beam spot on the ground is less than 20 centimeters. For the radars would be a few hundred meters. So there is no kind of ambiguity because of the terrain. So the terrain will not affect the measurements like it would with the radar. Okay. So just give you a sense of how well it works. The numbers that I have in this table here, it does not include the vehicle motions and effects. So if you put this instrument on a static platform and shoot the laser beam, we can get well over 10-kilometer range with this for each of the beams. In fact, like we go on the top of the building here at Langley, and we could even get signal from, there are some water towers that we can bounce the laser beam back around 15 kilometers away, and we get pretty good signal. In terms of the velocity, it can measure velocities along each of the beams to plus and minus 218 meters per second. The vehicle could be even traveling faster than that because the line of velocity would see the vehicle velocity that's projected onto the line of sight. So the vehicle could be traveling 400 meters per second, and we can still measure the velocity. The precision is very precise. I mean, we can do 2 millimeters per second in velocity, and for range 12.5 centimeter, and it outputs data at 20 hertz. Now, of course, these numbers going to be affected by the vehicle dynamics quite a bit. The range could reduce, and so as the noise on the measurements. I got the dimensions here, so you get a sense of what the size is, and the chassis is about 13 kilogram, and the head 2 kilograms, about 2 kilograms, and 78 watts of power.
I have a question from somebody in the audience. Actually, they had asked a previous question too, so sorry for getting to that. Their question was, is this a system that could work on a helicopter? They're interested in more information about that. And also if you have flown this over open water, perhaps.
Yeah, well, of course, for testing this, we've done a bunch of helicopter tests, but the water thing is interesting because if we have still, water like lakes and stuff, we get absolutely nothing of it. The water would act like a mirror. We need a rough surface to get signal back. So it won't work over water. unless the water is choppy and has foams and waves, and then we will get signal. Now, we have not on purposely tested this over water. We had situation that we have gone over like lakes and water channels with still watered, and pretty much got the signal just dies. I hope that answers your question. Okay. To validate the requirements and characterize the performance, we do a lot of testing. We've done a lot of testing, aside from the one I showed you in that slide with the aircrafts and those rocket-powered vehicles that we did. One of the tests, that was designed to get the velocity all the way, so we can show the maximum velocity we can measure, was a rocket sled test. I'm talking about this because that was one of my favorite tests. It was quite fun to do this. We went to China Lake. They have this. You can see the picture on the left. There's a track that is pretty long, more than 6 kilometers long, and very straight, where we put the NDL, and we had those 3 telescopes or lenses pointed to that rocket sled, and then on the right you see that the sled itself, and we put a target on it with some rockets that's gonna shoot it down the track. First, we were gonna put the lidar on the rocket, and then when that sled travels over the track, it wobbles to left and right quite a bit, so we couldn't get the beam on a target. So that's how we did it this time, like this. This was to get the maximum velocity. I can show you a little video. It's pretty short. So they use a bunch of rockets that here we go, send it down, and we are on the other end measuring it. So kind of getting both maximum range and the maximum, well, not maximum, but long distances measurement with this. So we did a lot. No, that was just one of the tests. There were a lot of tests like that. But I mentioned that the performance is affected by the vehicle dynamics. The main contributor to performance degradation is the vehicle vibration. Remember, I mentioned that all the signal processing is done in the frequency domain. And then if in the presence of vibration, the frequency spectrum of the laser is going to broaden. So the signal that we are trying to process, that's going to broaden. And, like in Pilates shows, if there's no vibration, you get nice Lorentzian shape spectrum. And then with the vibration, it's going to get shorter and fatter. So it's shorter, so we have less signal. That reduces our maximum range. It becomes fatter, and it affects the measurement precision.
Hey, Farzin, before you move on to the next slide, we have one question. Can you comment on how accessible the NDL technology is for the near future? Is it basically COTS, or does there a mix of government off the shelf GOTS type of stuff? And basically, do you think this is going to be accessible for the general consumer, etc.?
Yeah. Well, okay, you're jumping ahead, but I go ahead and answer that. Yes. So, like I mentioned, we built these ETUs, we delivered them. They're going to go on a couple of lunar landers, and that would be a kind of a demonstration for the follow-on landing missions. Even for those missions, we are going to be in closed loop with the vehicle. On one of them, we are actually a critical sensor. Now, this technology has been licensed to a company here in Hampton, Psionics. Psionic is commercializing this. So they build more copies of these units for other landing missions. They're also been building and marketing this system for aircrafts and ground vehicles. So the short answer is yes. You can reach out to Psionic, and for this for, for this technology. Of course, there are, this is a very new technology, so it's not like they have quantity productions in place, right? So there are still, um, it's the earliest stages, so it's not like there would be cuts and you just order 5 of this and you get them, in 2 weeks. But the avenue is there, and yeah, the answer is yeah. Okay. So many other questions? Okay.
No, that's it for currently. Please keep going.
For now. Okay. So let me move on. So since vibration was such a major factor in defining the performance of the system, and we're going to be, no matter what, even in aircrafts, we're going to be on a vibrating platform. So we devised a test where we essentially put a vibration test facility at Langley Air Force Base here next door at the end of the runway. And you can see on the east side of the runway, there's a picture there, it shows a tent where inside the tent, that's a vibe facility there. We put the chassis on a vibe table, and then the fiber cables comes out of the tent. It goes into the truck that's parked next to it. And those three um, lenses are inside that truck. Okay, shooting down the runway. On the runway, then we have another truck, and I have a picture on it on the right. In the back of that truck, it's not very clear here, but there is a big target, a big, like 6 feet, 5 feet in dimensions. But it's a diffuse target. So we shoot the laser beams to that target as this truck drives down the runway all the way to the end. So we can get measurements over, extended range from, a few hundred meters all the way to close to 4 kilometers. And then, we can see the effects of the vibration on the measurement. Here on the top left plot, the blue plot shows when there's no vibration. So you can see the signal intensity as a function of range. Of course, the signal drops with range. And then the other plots are with the presence of vibration, different levels. And you can see that, yeah, it drops, the signal drops. And that effect of the vibration gets worse with range. So you can see the separation of the blue plot with the other one is getting larger as we go down the range. This data goes to 3.5 kilometers. This was important measurements for us to do because we also needed to estimate what would be our operational range when we go to the moon. On this plot, the black dashed line, that's the detection threshold. We're shooting down the terrain, 3.5 kilometers, we still have plenty of signal to noise ratio. But we can put the LiDAR equation fit to it and then extrapolate it to see how far longer we can go. And that's a plot below. You see the fit of the LiDAR equations to the data with the no vibe. And then we include the effect of the vibration, and that's that blue curve that's fitted to the vibe data. And you can see that the red without the vibe, it goes well up beyond 10 kilometers. But the blue crosses the threshold as about 7 kilometers, quite a bit of reduction. And then the red is where we take out the effect of the atmosphere and adjust it for the lunar surface albedo and surface reflectivity. It still comes to about 7 kilometers. By the way, when we were designing these EDUs, we underestimated the effect of the vibration, especially that it amplifies with range. That part, we weren't quite had the physics under control. So for the next one, we're going to make sure that the way its chassis is designed, that the laser is more isolated from the vehicle vibration. So the effect of the vibration is reduced. On this one, I plotted the range data from when that truck was a little over 3.5 kilometers, and you see a nice solid line. That's a range data. And then when we shake the chassis, you can see the range measurements gets noisy. Okay, of course, higher the vibration loads, larger errors. And the velocity is the same thing. So remember the 2 millimeter per second on the velocity and 12.5 centimeter range I mentioned? Those noises for the range will grow from 12.5 to 3.8 meter at 1 kilometer and almost 15 meter at 6 kilometers. The velocity goes from 2 millimeters to 3.8 centimeters per second at 1 kilometer to 15 centimeters at 6 kilometers. But I know we can improve this quite a bit if we're just isolating that laser from vibration, phantom vibration. Still, these numbers are more than an order of magnitude better than radar. So they're still very good. Here I just have the error budgets. On one side of the tree, I have the precision, and the other side, I've got the bias errors. Under the precision errors, vehicle vibration is the dominant factor. We talked about that. On the bias is the beam pointing. So if we don't have a good knowledge of where the laser beam are pointed, we're going to have a bias error. So we spend a lot of time doing some testing and a lot of analysis to get an estimate of how much would be the knowledge error. One of it is how well you would register the pointing each of those beams to the vehicle reference frame. And then there are changes on the vehicle too, right? The thermal expansion of the optical head itself, and then the vehicle, have thermal expansion, or it would flexes when it's in a low gravity environment. So we estimated it. And what I have on this slide, if you just look at the bottom of this slide, the bias error for the velocity, we put the maximum. This is the absolute maximum, because these errors would scale with velocity and altitude, okay? So at maximum velocity and maximum altitude, those bias errors are about 13 centimeters per second for velocity, 1.3 meter for range. But it's very important to register these beam pointings relative to the vehicle. So now, including the effect of the vehicle, I got the specs here. So when we go to the moon for these ETUs, we're going to have a range of 6 kilometers. The minimum velocity we can measure is 0.1 meters per second, and maximum, like I mentioned before, 218, 20 hertz rate. These noise and bias errors that I have here are the max, right? At 6 kilometer and maximum velocity. So we are still talking about 15 centimeter per second noise and 13 centimeter per second bias. And the range also the same thing, going 15 meters in noise and a little over 1 meter in bias. Okay, so there was earlier questions about their applications. So I listed some here. These applications that I've listed here are the one that we've done studies, testing, and I mentioned Psionic that is commercializing this. They are pursuing these also. One is the aircraft navigation in GPS deprived environment, right? Because we are providing altitude and velocity. So, but there is another benefit. Even if you have GPS, this data would be more precise than what GPS can tell you. And also it's going to be relative to the local ground, right? So if you get altitude relative to the ground, so it's a different data product that comes out of this sensor than GPS. Brownout condition, landing in a brownout condition is another one. That one we actually did a helicopter test with Army right here in Fort Eustis. They wanted us to help them with that. The idea there is that the NDL gives such a good velocity and altitude relative to the ground that as you're approaching your landing area, if you have a very good state vector knowledge, you know exactly where you are, how fast you're going, where you're going, then by the time you get to the landing area and you emerge into the dust and you lose visibility, you know exactly where you are. You know, one can imagine that you would even kind of have a synthetic display for the pilot to look at the ground instead of not seeing anything through the dust. Autonomous ground and vehicles, that's actually one of the main reasons Ionic licensed it. This is for driverless cars. It would be a different version of this. It would be much smaller, much shorter range, and would have to have some kind of a scanning mechanism because you have to around the car, you have to do a 3D image of all the surroundings. We also generate a velocity map of everything, so not only where the other cars are, if they are coming towards you or driving away from you. The same for air. The last one, exploration, like oil and natural gas exploration. Oh my God, we did a lot of tests with that one. Did some flight here in the States, in Canada, in Australia. This is actually pretty interesting because the idea there is that you can fly a small airplane and with a gravitometer to measure the subtle changes in the gravity. So if there are things under the ground, oil, natural gas, or other things, there will be a little change in the gravity. And if you can measure that, then you can detect these resources under the ground, right? The problem is the motion of the aircraft. You can't really control or measure it. So the idea there was that to use the NDL to get a very precise velocity data relative to the ground, so you can take out the effect of the motions of the aircraft and measure that gravity changes more accurately. So that was, I thought, was pretty interesting. Yes.
Before you move on to the next slide, there's a sorry. Go ahead. Finish your thought. I'll ask the question.
No. Go ahead. No, please go ahead.
So our question is, you're talking about potentially using it for gravimetric analysis and stuff, but how affected is this technology, LiDAR specifically, affected by weather conditions? I mean, is there a way that you can mitigate effects of weather conditions?
No. This is one area that radar is superior to LiDAR. The system is affected by weather. Now, the effect is attenuation of the return signal. Okay, so if there are precipitation, there's heavy fog. Fog is worse. If there's a heavy fog, the operational range is going to reduce quite a bit. Rain and snow, those also are going to attenuate it, but not quite as much because like the rain droplets, there's a lot of empty space between the droplets. But still affected by it. Worse is fog, and this LiDAR works at 1.5 micron wavelength, so it's a near IR, so it's a little bit better than visible. So with this system, a lot of times if we can't see the target, chances are that the LiDAR is going to have hard time getting enough signal. Of course, the remedy is, to have more power, increase it. But no matter what, this is affected by the weather. But there's another factor for like aircraft. Okay, you're looking from up down, so the effect of the atmosphere is a kind of less as you are looking if you're looking horizontally into the weather. So if you're looking up down, you're gonna see less of the weather effect. Okay. All right. Okay. This is my last slide, actually. I was just summarizing here. Then, I'll be more than happy to answer any additional questions. This is just saying, summarizing what I've been talking about, that the NDL is actually pretty considered pretty important for these landing missions that are being formulated, or even for like human landing on the moon, the Mars mission, Mars sample returns, or the other missions to like to Titan and Europa, places like that. It's a precision, um, but the radars gave these landing missions a lot of problems in the past, and the lidar, is it can mitigate a lot of those issues. Now next year, well, later this year, we're going to fly on 2 lunar landers. We are in the closed loop with the GNC system. On one of them, we are a supercritical sensor on one of those landing instruments. That's not how it started. They kind of tricked us. First, it was just, okay, we're just going for the ride. We're just going to go put it on those vehicles and just collect data and say, hey, this works. Now let's put it on a human lunar landing mission. But once we get there, the vehicle guys wanted um, uh, to use it in the closed loop. So it was like a we tricked into it. But I'm actually happy that happens. It makes these flights, these missions, even more meaningful. I talked about this vibration, the vehicle environment. Um, so the performance is dominated by that. And that would be the case for the aircraft, helicopters, and aircraft too. Um, but we have remedy for that for the future. To minimize those. Still, no matter what we do, the vehicle is going to be the dominant source of error. Um, the last bullet, we are continuing technology advancement for the next generation of the NDL. We are using some advanced component technologies like integrated photonics and non-mechanical laser beam steering, so we don't have to use 3 lenses, we just use 1, and can steer it in many, actually, instead of 3 different directions, we can steer it to many different directions. And those, well, we're going to make the system shrink quite a bit. And of course, we're going to, this effect of the vibration, we're going to get that reduced. I think so. This is my last slide. I really thank you for.
I think we have a few questions lined up for you, so I can start.
Yeah.
Absolutely. So I have a question first, which was about the missions that you're where NDL will be flying. These are the CLIPS missions that are happening later this year. Is that correct?
That is correct.
Which particular 2 groups you're working with, just so that we know, that, hey, NDL is going to be flying on this day and stuff. Which missions?
Yeah. So yeah, and this is the very first CLIPS missions, the first 2. One is Astrobotics. Astrobotic is in Pittsburgh, Pennsylvania. And the other one is Intuitive Machines in Houston. Intuitive Machines
sounds great.
yeah, you know, some of these projects we had in the past, like that very earlier slide that I showed you with the helicopter and aircraft test, and Morpheus rocket power test that we did. We did that with the collaboration with other NASA centers, many of them from JSC. So some of those guys are now at Intuitive Machines, so they have actually experience with this already.
Oh, that's great. We have some questions from actually it's from Samantha Applin. Samantha, do you want to just unmute and ask your questions? You do have quite a few, so I wanted to let you pick and choose which one you wanted to ask.
Yeah, sure. I was curious if there's any current investigations into the scanning mechanisms that'd be appropriate for the autonomous operation.
Oh, yes. Hi, Samantha. Yes. So yeah, we are continuing working on those non-mechanical beam steering, the liquid crystal that you worked on those a little bit. Um, so we have actually recently, these past 6 months or so, we got new sets of those devices from two different vendors, and we've been doing some testing with the NDL on those. We did some testing at Langley, where we could go up to like 800 meters. But this coming week, we are actually going back to the Air Force Base. Remember that one of those tests I showed you with the vibe table facility at one end? Well, we're going back to the same runway to test out one of those non-mechanical beam steering with NDL over extended range all the way to 4 kilometers.
Okay, thanks. And I was also curious if so the CLIPS landings, are that involving the lunar dust or
No.
the impact on system performance?
Oh, I'm sorry, you got cut off a little bit, Samantha.
As you're doing the lunar landings,
Mhm.
I assume there would be some lunar dust impact on the system performance.
Those two landers are relatively small. They are not expected to pick up the dust until they get like 6 feet above the ground. We are affected by dust also because, like I said, if you don't see through it, then you're gonna have hard time measuring through it. But by the time they get that low, they really doesn't matter. The measurements, they already know where they are, and nothing is going to change that much. The IMUs are going to be good enough to carry the rest in the last few meters. Even on the Apollos, the dust plume elevated to no more than, I can't remember the exact numbers for those missions, but no more than 10 meters. So even if we stop making measurements, once we go immersed into the dust plume, then that's where the measurements are going to be affected. By that time, then it really doesn't matter. The measurements are not that critical anymore.
Okay, thank you. And my last question was, in terms of the space applications, have the radiation tests been conducted on the system itself? Or okay.
Yeah. We did radiation testing on the component level, especially we focus on the fiber optics and photonic components, because a lot of the electronics already space grade. So, but yeah, we did some radiation testing on the components.
Thank you.
Mm-hmm.
So we have one more set of questions from Mr. Ali Hassani. If you want to, Mr. Hassani, if you want to unmute and ask questions.
Hello, thank you so much, Mr. Amzajerdian. This is AIAA Hassani from Virginia Tech Navigation Lab. My question has two folds, which are kind of, related to each other. One, based on the fact that you want to use this kind of LiDAR and its measurement in the space missions, I want to know Have you studied the impact of different type situation of sun illumination or sunlight uh, on the precision or accuracy of the LiDAR? For example, in the Artemis project, we are doing the mission in the poles of the moon. So definitely we have different type of the sun illuminations. And the second part of my question is about the brownout situation, like the using the light, this type of LiDAR on helicopters. I just want to know the velocity that the LiDAR show to us. Is it possible that we measure the dust velocity rather than the vehicle velocity? Because I know some of these FMCW LiDARs that are using for autonomous cars are measuring mostly in a dust situation the velocity of the dust rather than the correct vehicle velocity. Thank you so much.
Yes, Ali, excellent questions. Okay, let me start with first one, sun illumination. All right, so, okay, twofold to that. Of course, when we are in space, we're going to be in extreme thermal environments. So, so some illumination from a thermal standpoint is a consideration. We need to keep this instrument over a temperature range to survive. We don't want to cook everything, and but it's a pretty long, big range. It's just the same as like any other electronic instruments. And then operational, the same thing. There's operational range that we can operate, and this for these ETUs, that's around 0 to 45 degrees C. So there are considerations when we go in there to make sure that we stay within that temperature. Now, but I think your concern, your question is more the effect of the sunlight on the measurement itself. If the sunlight make it to the detectors, to the receiver, and the answer is no. This is essentially a coherent LiDAR. Um, there is almost no field of view for those lenses. Like when the beam comes out of those lenses are almost perfectly collimated all the way to the ground. Okay, so anything beyond that, the lens will not see. So sun, looking into the sun is not a concern to us. We can also think of it that this has such a narrow uh, band filter that you just don't see the sun. In fact, one of the reasons that this technology is important for driverless cars is that the other type of lidars or radars, they are affected by the sensors that are on the other cars, and you cannot, it messes things up. With this system, there's no possibility if you have this lidar on one car that's going to be affected by the lidar that's on the other car. There's almost no the probability of the other beams making it to another one is extremely small. Okay, I hope I got that first part. Now I'm trying to remember what was your second question.
I asked about the dust and the impact of the
Oh,
dust.
okay. So I did not actually. I should have put this on this slide. One of the ambitions that we have is to include measurements of the wind velocity with the same instrument. And the way to measure the wind is that to get the signal from the dust that are the natural dust that are in the air, the aerosols. And we've done that. We do that at NASA Langley. We measure wind velocity with LiDAR, but there are bigger instruments. So even on the dust plume, like in the case of a helicopter or when we are landing on the moon and we pick up dust, there are ways we can get around it. And so imagine this. You remember I mentioned that every signal processing is done in the frequency domain. When the light hit some dust plume, it's gonna get the signal back. This is an extremely sensitive sensor. So we do get signal back. And then if those particles are moving, it's going to cause a Doppler shift, and we can measure that. In fact, we tested that in the lab with this system, with a can of air, the air that you use for cleaning your keyboard, with that, and we could measure it, but but it was just a test in the lab. But it's quite possible. Also, if for those cases, if you go through some dust plume and then some of the light is still going to make it to the ground and come back, then in the frequency domain, you're going to have two distinct signal in frequency domain. One is going to be from the dust and one from the ground, and you can separate them because they're going to be different frequency. The ground is not moving while the dust is moving, so it's different frequency. Yeah, so that's yeah. Okay, I hope I answered your question there.
Yes, thank you so much.
In the interest of time, we'll probably end the questions now. And I wanted to thank Farzin for, again, sharing the work with us. I also wanted to let people know that we have another, hopefully you guys can see my screen. Are you guys able to see my screen, or are we still seeing Farzin? Oh, I guess it doesn't really matter. We have a series of, perhaps that's what it was that you have to. It seems like I'm having some technical issues. I wanted to let people know who are joining this meeting that we are starting this as a series of seminars. So Farzin's the first in 2022 of a long line of people. We have our next talk on April 22nd, where Tom Horvath and Jennifer Inman from the SciFly project are going to talk about chasing spacecraft. And I think Farzin was just talking about how at NASA Langley, we're able to use LiDAR to measure winds. That's actually one of the capabilities that SciFly has. So you should be able to hear a little bit more about LiDARs, but really also about some of the cooler instrumentation that SciFly does on April 22nd. And again, thank you so much, Farzin, for coming and talking to us.
No, thank you so much for the opportunity and your time. Thank you so much.
Thank you. And we'll post the recording online. So if anybody wants to catch up later, you will be able to. Thank you again.
All right. Thank you, Sam.